Okay, so our next speaker is Shuailiang Ge from KAIST, South Korea, and he will be talking about detection of ultralight dark matter using radio telescopes and satellites. So I will send you a reminder when 5 minutes are left.
Okay, thank you. So I'm Shuailiang. I'm currently a postdoctor at KAIST. And first, I would like to thank the organizers for inviting me to give a talk in this seminar. This is my current location in South Korea, and the city is called Daejeon, and the KAIST is the name of the university. Okay, the topic of my presentation today is about detecting ultralight dark matter using radio telescopes and satellites. And the first, I will give a very brief review of dark matter. And I think most of you are very familiar with this concept, so I will do this part very quickly. And we know that dark matter accounts for about 1/4 of the universe's total energy. And there are a lot of evidence for the existence of dark matter. For example, the observation of the galaxy self-rotation curve has a very difference with that predicted from the Newton's law. And as you can see from the figure, that there's a big discrepancy, and this big discrepancy can be explained by the existence of a large amount of invisible matter. It's called dark matter now. And another example is from the collision of two galaxies. And you can see that the distribution of the total mass and that doesn't match the distribution of a visible of the visible mass. So this also implies the existence of dark matter. And another evidence for the presence of for the existence of dark matter is from the CMB observations, and people can infer the dark matter information from the CMB anisotropies. Okay, and what do we currently know about dark matter? Well, and the mostly acceptable model now tells us that dark matter near the solar system, dark matter density is roughly 0.3 gigaelectronvolts per centimeter cubed. And it follows the Maxwellian distribution, and the velocity near the solar system roughly 10 to -3 speed of light. It is non-relativistic. Okay, so currently we know that the dark matter only interact with the standard model via gravity. Does it have any other interactions? We don't know. And because of this, people have invented a lot of dark matter models. And the mass of a single dark matter particle, if I can call it a particle, can span dozens of orders of magnitudes. And the lightest one can be as light as 10 to -22 electronvolts. And the heaviest one can be as heavy as dozens of solar masses. And the traditional dark matter candidates is called the WIMP dark matter. And a lot of several groups have put a lot of efforts to search for this kind of dark matter, but there's no positive evidence yet. And instead, the parameter space for the WIMP dark matter becomes narrow and narrow. And due to this, people become more interested in looking for other possibilities, such as the ultralight dark matter. And the ultralight dark matter, they have such kind of dark matter particles are very light compared with the traditional WIMP dark matter, and so they have a very huge number density, and they can be treated as classical waves, and you can also call them wave dark matter. And famous candidates of this kind of dark matter is dark photon and also axion. And this talk will focus on dark photon. Okay, so what's dark photon? Dark photon may be one of the simplest extensions of a standard model. You just need to extend the standard model by a U1 gauge, an extra U1 gauge. Some people usually call it the dark U1 gauge, and the corresponding U1 gauge boson is called the dark photon. It's just like a twin of our standard model photon. But the dark photon can have a mass, and the mass can come from the Higgs mechanism or Stickelberger mechanism as one special case of Higgs mechanism. And also, the dark photon has a coupling with the photon, and this term is called the kinetic kinetic coupling term. And this is usually this is the only part for dark matter to couple to the standard model. And epsilon should be very small. That's the reason that dark photon behaves like a dark matter. And usually on the phenomenological side, when we search for dark photon, we don't care so much about the model buildings, and we simply treat the kinetic coupling constant epsilon and the dark photon mass ma prime as two free parameters. Okay, so for convenience, we can do a redefinition of the fields by rotation, and that means we change the basis. So in the so-called mass basis, we see that the kinetic mixing term f prime term is gone, but the price is that we get a new term that the dark photon field couples with the electric current. And due to this term, we say that the dark photon induce an effective electric field, and you can call it a dark electric field. And the strength of this electric field is suppressed by the epsilon. And this electric field is very small, but we have figured out a way to detect such a small electric field. And the way is to use the radio telescopes. We know that on the Earth, people have built a lot of radio telescopes for astronomical observations, and this radio telescopes use antennas to collect radio waves, and the antennas are usually made of metal. For example, consider the simplest antenna, the dipole antenna. They are the dipole antenna represented by the two black bars in this plot. Okay, they are made of metal. And when the dark photon dark matter comes, and the effective dark electric field will drive the electrons inside the bars to oscillate. And these oscillating currents, electric currents, will be recorded by the detector. So this is one way to detect the dark photon. Dark photon induce the oscillating currents just in the same way as the standard model photon does. But the difference is that the strength is much smaller, okay, suppressed by the epsilon squared, actually. And there's another common type of antenna called the dish antenna. So here's a photo of the dish antenna of the FAST radio telescope. FAST is currently the world's largest single dish radio telescope. So the diameter of this dish antenna is roughly 500 meters. So it is huge. And for the dish antenna, we can do similar analysis. So we take a small element on the surface of the dish, and when the dark photon dark matter comes, they drive electrons to oscillate, and these oscillate electrons will emit electromagnetic waves made of standard model photons, right? So that means the basic picture is that a lot of dark photon dark matter comes. Most of them will just pass through the dish antenna freely, but a tiny portion of them will be reflected in the form of standard model photons, and these reflected photons will be detected by the detector put in the air. Okay, and one interesting feature is that no matter in which direction the dark photon comes, the reflected photons will always be in the direction perpendicular to the local surface of the dish antenna. This is just because of the boundary conditions on the surface of the metal dish, and because the dark photon is non-relativistic, and after it converted to standard model photons, the momentum in the direction perpendicular to the surface will inherit most of the energy from the original dark photon. And so that's the reason why the reflected photons will live in the direction perpendicular to the local surface, just because of the matching boundary conditions. Okay, so now what's the best shape to detect dark photon? The answer is simple, just the sphere, because the sphere will concentrate the reflected photons on the center of the sphere. But unfortunately, we know that for astronomical observations, people usually build the dish antenna in the shape of a parabolic shape, in a parabolic shape. And this is good for us because they want to collect parallel lights and concentrate them on the focus of the parabolic mirror. But parabolic mirror will not concentrate the reflected photons from dark matter. And this will greatly decrease the sensitivity. But as we will see that even using parabolic dish antenna, we can still get a very good sensitivity on the dark photon. Later, I will come back to this point. And I should say there's another type of radio telescope. People just simply collect many antennas together, and these antennas can be either dipole antenna or dish antenna, and they form an array. And the famous example are the LOFA array or SKA array. Okay, so one feature of we can similarly calculate the dark photon dark matter signal when they hit these arrays. And the feature is that the signal will be greatly suppressed if the distance between two antennas is larger than the dark matter wavelengths. Okay, so next I will talk about the detection ability of radio telescopes. On one hand, we can calculate the electromagnetic flux induced by the dark photon dark matter, and the result is simple. The signal is proportional to the dark matter density and suppressed by the coupling squared. And we also divided by the telescope frequency resolution because we want to express the signal in terms of the spectral flux density. And one feature of the signal is that it is nearly monochromatic. The dispersion is very small. This is because the dark photon dark matter is non-relativistic and it has a very small dispersion of velocity because it follows the Maxwellian distribution. Okay, so the signal is nearly monochromatic. And on the other hand, we know the minimum detectable flux of a radio telescope, and it has the following expression, and it depends on several parameters of the telescope itself. And this is part of the physics of a radio astronomy. Okay, and what we do is just we equate this equation with the dark matter induced flux, and then we can get the minimum detectable epsilon. And we see that it is proportional to the dark matter density and also proportional to the SEFD, which is the system equivalent flux density. And the important thing is that the better frequency resolution you have, and the longer observational time you have, and then you can detect the smaller epsilon. Okay, and the real data we use is from the FAST telescope. As I have mentioned, FAST is currently the world's largest single dish radio telescope, and it currently it currently works in the frequency range 1 to 1.5 gigahertz. It has a very good frequency resolution. It's about 7.63 kilohertz. And after we have this fast data, we did some data analysis. And because we know that the dark photon induced signal, the dark photon induced signal is a constant with time. It does not change. So we can do the data cleansing by filtering out some large frequencies. And we do this for every frequency being. And this is the result after data filtering. Okay, and this is give us a very stable background, so we can use it to search for monochromatic signal, or reversely, we use this data to make constraints on the dark matter parameters. And this is our result. And we use the fast data, and we get some very good constraints on the connect mixing parameter epsilon, and in the frequency range 1 to 1.5 gigahertz. And we see that is better than the previous CMB constraints by about 1 order of magnitude. And this dashed red line is the projected sensitivity of the uh, of the fast in the future, because the fast will be upgraded in the future. It can work in a larger range of frequency. And this blue and brown dashed lines are the projected sensitivities of LOFA and SKA. We can also see that they can receive, we predict that they can receive, they can give us very good sensitivity on detecting the dark photon dark matter. Okay, this is just this is the first mechanism that I have talked, and it is based on the fact that when dark photon dark matter comes, they will interact with the metal dish. They will drive the electrons in the metal dish to oscillate and emitting the electromagnetic waves, and can be detected by some receivers installed on the radio telescope. And next, I will introduce you a different mechanism. That is, the dark photons can resonantly convert into photons in the plasma environment. Okay, and again, we start from the Lagrangian, but now we choose a different basis for convenience. And this basis is called interaction basis. And after a field redefinition, we can clearly see that the interaction between the dark photon field and the photon field. And if you draw the Feynman diagram, it's just simply a one-to-one process. And the coupling strength is epsilon times the MA prime squared. Okay. And so this means that photon and dark photon can convert to each other. Okay, to get the conversion rate, and we solve the equation of motions for both for the photon and dark photon, and we see that they are connected by they are related by this mixing matrix, and the off-diagonal elements are non-zero. This is reason that they can convert to each other. And we know that if two diagonal elements equal each other, the conversion rate will be maximized, and we call it the resonant conversion. We know that dark photon can have a non-zero mass, but how about the photon? We know that photon is massless in vacuum, but it could be massive in medium, such as plasma. So in the plasma environment, there's a chance that the photon mass equals the dark photon mass. Then the conversion rate will be maximized, and this is called resonant conversion. So now the question is, where is the plasma? Sorry, I should briefly mention why the photon will acquire an effective mass in the plasma. This is just because its interaction with the plasma particles, and the effective photon mass is just the plasma frequency. And so the resonant conversion is just when the dark photon mass equals the photon mass, and then equals the plasma frequency. So the question now is, where is the plasma? The answer, here's some details about how to calculate the probability. And okay, so by solving the equation of motion, we can formally write down the conversion probability in this way. And then we apply the saddle point methods to solve this equation. And this is our result. And we can further get the conversion power, and with some geometric factors taken into consideration, we can get the signal strength. And with this expression. So now we know the signal strength. Now the question is where to find the plasma to make such resonant conversion happen. And the good source of plasma is just the sun. And the picture is that when the dark photon dark matter comes passes through the sun. And in the plasma environment, there is a chance for them to resonantly convert into photons if their mass, if the mass of dark photon matches the plasma frequency. Okay, and to be more specific, these two plots shows the density, shows the profile of electron density in the solar plasma, and the left figure is the plasma in the solar corona. The horizontal label, the horizontal axis is the distance, is the head from the solar surface, and this is the region of the chromosphere, and this is the region of corona. And we see that the vertical axis is the electron number density. We see that the electron number density spans a large range. Okay, and we can go further away from the sun into the location of the Earth and even beyond. The plasma is still there, but in the form of a solar wind. And the number density of electrons are much lower compared with that in the corona. Okay, note that here the 10 to 8 and 10 to 8 is here. Okay. Then how to collect the photons converted from the dark photon. And we use the satellite called the Park Solar Probe. And Park Solar Probe is actually the first and the only man-made satellite that can venture into the solar corona. So this is the Park's orbits. And the closest approach to the sun is roughly 10 solar radius from the sun. Okay, and the furthest point is at the Earth's orbit is 1 AU, and we can map the orbits in this plot. And this is note that this is the closest point to the sun is roughly 10 solar radius, and this is the furthest point at the position of the Earth. So this means that the Parker Solar Probe can scan the plasma frequency in this range, and if the dark photon mass locates in this range, it is resonantly converting to photons, and the signal can be locally observed by the satellite, by the Park Solar Probe, without the distance attenuation. Okay, and actually, to be more specific, the Park Solar Probe carries two different receivers, and together they cover a large frequency range represented by this blue line. Okay, and if the dark photon mass locates in this range, they can still resonantly convert into photons, and they can still be detected by the satellite, but it will suffers from the distance attenuation. Okay, and we have modeled the density profile, electron density profile with this formula. And if we plug this formula into the expression of the signal strength, then we can know the strength of resonant conversion at different points between the sun and the Earth. Okay, then we use the data collected by the Park Solar probe to make the constraints, and we see that our results, like this blue line, is the constraints made using the Park data. We see that our result is about two orders of magnitude better than the previous constraints from the CMB. The main reason is because that the dark photon, the Park Solar Probe can go very close to the sun, and they can detect the converted photons without the distance attenuation. This cannot be done by other satellites like a stereo. Stereo is we also use the stereo data to make constraints. We see that it is much weaker than the Park case because the orbit of stereo is fixed at 1 AU, so it suffers from a large distance attenuation. And the advantage of the Park Solar Probe can be seen more clearly in this picture, that as the Park gets closer to the sun, and that means that it gets closer to the location of resonant conversion. So it becomes more powerful in detecting the converted signal from diphoton dark matter. And this is especially useful for detecting heavier diphoton. Okay. And also we can compare our result with the LOFA. LOFA is the radio telescope array on Earth, so it suffers from the large distance attenuation. But however, LOFA has a very good frequency resolution, so we can still use LOFA to get a good sensitivity on the diphoton dark matter. So we see that our constraints using LOFA data still better than the previous result from CMB constraints. But note that because of the radial window of the Earth's atmosphere, LOFA works at the frequency lower than the PARC. So basically, PARC and LOFA they both provide constraints on diphoton, but at different radio frequency ranges. So this is nice. So we can search for diphoton dark matter in a wide range of mass. Okay. And in addition to the dark photon, axion can also resonantly convert into photons in the plasma environment. But for axion case, it requires the presence of a non-zero magnetic field. But because the solar magnetic field is not strong, it's actually very weak. In the solar corona is roughly about 1 to 4 goes, and is a weak field, and so the conversion rate for axion to photons is not very strong, and our constraints is not as good as the diphoton case. Although it surpasses some terrestrial like experiments, but it's not comparable with many other astrophysical constraints. So we see that this mechanism only works well for the dark photon case. Okay, I think I finished my talk and make a short summary here. And I want to say that dark photon dark matter can be directly detected by radio telescope or radio satellites, and basically based on two different mechanisms. The first mechanism is due to the interaction between dark photon and the mantle antennas. The dark electric field will drive free electrons to oscillate, and these oscillating electrons will emit electromagnetic waves. And electromagnetic waves can be detected by the receivers on the telescope. And another mechanism is that diphoton, it happens far away from the Earth in the solar plasma, and diphoton dark matter can resonantly convert into photons if their mass matches the plasma frequency. And we want to say that the PARC solar probe is ideal for detecting such signal because they can venture into the solar plasma and observe such resonant conversion locally without a distance